Hi, this is a recorded lecture for the IB DP Design Technology Structural Systems A3.2. This is HL content and it is design in theory. And today what we're going to be looking at is structures and structural systems. Let's start with this. There are natural and man-made structural systems. So for instance, if you watch this video here, this is a video of this guy who's putting crushed car on top of eggs. And so these are eggs down here and they are holding up the car. I'll give you the spoiler alert. They're holding up the car without cracking. This is a very large crane that is lifting a very large tower. So this would be a man-made system. The eggs would be natural structures and natural structural systems. Now, the IB wants you to know this, that structures are fundamental to both the natural world and the built environment, designed to support loads, provide stability, and maintain their shape under various forces. Designers must analyze structures to understand how forces act upon them, select appropriate materials, learn from natural designs, ensure safety and durability, and identify the best structural types, this is either frame, shell, or solid, for their creation. This analysis provides insights into effective design principles and fosters innovation for stronger, lighter, and more effective products. Let's talk about some of the structures that you'll need to know. So first one is a frame structure, and this is formed from a network of connected parts. This might be beams, rods, or tubes, and they're often lightweight and strong in multiple directions, and you commonly see them in things like bicycle frames, greenhouses, or scaffolding. And so this is scaffolding right here, and these are a greenhouse frame. And you would cover this over with plastic or a shell. We'll talk about those right now. The next type of structure that we want to understand are shell structures, and these are characterized by a thin outer surface that holds its shape and supports weight. They enclose space and are often curved or domed for strength, and they do not require an internal frame. Examples might include crash helmets, car bodies, and eggshells. So you can see here's a crash helmet right here. This is actually a very famous shell structure. This is the Pantheon in Rome, and it is a concrete dome, and you can see that it's based on a circle, and it is very strong. It's withstood the forces that want to tear it down for about 2,000 years. This is another example of a shell structure. So this is an inflatable concrete structure, and essentially what you do is you inflate it. So you blow it up with an air pump, and then you spray it with water, and it will harden and form these nice structures. And these are really good for, say, in a disaster where you need some quick shelter to go up. It's very interesting. Please do watch this video. The third type of structure that we want to concentrate on are solid structures. So these are made from a solid mass of material, and they rely on their weight and bulk for their strength. They're heavy, dense, and very strong. And you can think of things like concrete bollards or big metal or concrete sculptures or tree trunks and things like that. And they get their strength from just being dense and strong and having a lot of material. Now, most of the types of structures that we see are actually a combination of these types of structures. So for instance, here's a frame and it's got this shell on the outside of it. You can see right there. And they provide a robust, lightweight, and functional product. Cars combine a metal frame. They have a shell body panels. So designers must understand how different forces act on structures to ensure their stability and prevent failures. These forces can be static, that means they're stationary, so essentially they are the structure's own weight, or they can be dynamic, which is things that move. So for instance, wind or vehicles or that kind of thing. This is an example of dynamic forces. This video right here is showing a hurricane and a building and how they interact. You don't need to watch the video because essentially you can see what happens when the wind interacts with this building, ripping its roof off. Now, these are the types of forces that we want to consider when we build a structure. So we need to consider compression, tension, bending, shear forces, and then torsion. So compression is a squeezing force. You can see right here where you see press. So think compression, pressure, pressing. And it's a squeezing force that shortens a material. So this could be, say, a brick pillar supporting a roof. And this is how it's calculated. You need to understand that it is the total vertical load, which is the force in Newton, divided by the area that it acts on, which is in meter squared, and in metric, that is a Pascal, which is newtons divided by square meters. So you don't really need to know how to calculate these, but you're going to need to be aware of, for instance, the unit. And I would like you to just kind of think about this. Remember that force is a push or a pull, and area is, length times width. So you're really paying attention to how much force is applied to a specific area. And different materials are going to act in different ways. So elastic materials will bend or deform, whereas rigid materials might not. They may just break. A classic example of this is a suspension bridge. So if we think of a suspension bridge, it has these cables which are under tensile force. We'll talk about those in a minute. And then you've got your compression force, which is, for instance, these pillars that the bridge is being held up on, and those are squishing the actual bridge itself. So that's the compressional forces right here, squishing these concrete pillars. Tension is a pulling force. So this is the example of those bridge cables right here. So they're being pulled. The roadway here is actually pulling them down, and the weight of everything, the cars and trucks that are going over that. So that's tension. Tension is a pulling force. It is also measured in newtons over meters squared, so that is pascals. This is an example of Young's modulus. We'll talk more about these. These are stress and strain graphs, and you can see this is actually showing tensile force being applied to a material, and you can see how it stretches, and finally fractures. Torsion is a twisting force, so you can think of a screwdriver twisting in a screw. It's calculated by multiplying the force in newtons times the distance from the axis. So the distance from the axis would be the bolt. In this case, this is a nut. So the bolt would be the axis, and the distance from the axis to however far it goes out. So for instance, the length of this wrench. So it's that force times distance, and that is a Newton meter. Bending force causes a material to sag or curve. You can think of a bookshelf loaded with books, and it's calculated by bending moment, which is force times distance, and this is also measured in Newton meters. You can see here, this is an I-beam that I created in Fusion 360, and I ran a finite element analysis on it, and you can see that it is bending. And this is an interesting force in that you have compression on this side of the I-beam. This side of the I-beam is being squished or pressed, so it's under compression. And on this side, you're getting tensile or pulling forces. So this is actually being pulled on this side and pushed on this side. So compression and tension all in one. And again, that's measured in Newton meters. When we talk about shear, we're talking about two opposite and equal forces acting on an object, but they are not aligned. This causes a cutting or splitting action, and you should think of scissors cutting paper. And this is force divided by area, which is a Newton. So that's the unit that you would use. And you can think of it like this. You see that these are acting in opposite directions, and then you're going to get the shear or cutting or splitting type of reaction when you have a shear force. Thank you for watching.